solar masses and cooler than 17 million Kelvin. The process begins with the creation of deuterium from a proton and neutron. Neutrons are readily present under most circumstances, but do form in the tremendous pressure of the inner star. Normally, excited atoms' electrons are free to jump to higher energy levels upon significant collisions or other energy transfers. However, in the violent environment of a star, the density restricts these levels. Rather than having a probability of being quite distant from hydrogen nuclei with no chance of being near a proton, electrons are forced by electromagnetism to what is normally their lowest energy level, where there is a chance of coming in contact with the nucleus. When an electron is naturally at this lowest energy level, it doesn't have the extra energy needed for binding to occur between itself and a proton. However, when the energy levels are so restricted by the pressure of neighboring protons, W and Z bosons can come into virtual existence and facilitate the binding of the electron and proton to yield a neutron, positron, and electron neutrino. Consequently, the positron and a nearby electron collide, annihilating each other to create two gamma rays, whose energy is diffused by the interstellar matter until it escapes. Adjacent protons need to overcome the Coulomb barrier to get close enough for the aforementioned fusion to begin. Because neutrons are normally bound by the strong force within the nucleus of an atom, if they don't bind with a proton quickly, they will undergo beta decay, again facilitated by W and Z bosons, but this time releasing the energy originally used in binding to yield a proton, electron, and anti-electron neutrino. The energy is conserved in the kinetic energy of the three resultant particles, particularly in the kinetic energy of the anti-electron neutrino. Again over